Welcome to the deep dive. You know, uh, we spend our entire lives surrounded by walls that are, well, they're essentially humming with these silent, invisible rivers of power.
They really are.
You wake up, you push a button, and instantly a metal coil in your toaster just glows red hot, or
Right.
you flick a switch, and a glass bulb completely floods the room with light.
Yeah, and we just expect it to work every single time.
Exactly. And I mean, at the end of the month, you pay a bill for this privilege without really questioning the underlying mechanics of what you are actually buying.
Right.
So today we are tearing into the physics and, the actual engineering of everyday electricity.
Hmm.
We're moving past those middle school diagrams to look at the raw atomic realities of the grid.
Which is a huge paradigm shift.
It is. The mission here isn't to rehash the basic definitions you already know. The goal is to completely change how you perceive the walls of your house, the devices you rely on, and ultimately the reality of that monthly utility bill. We are decoding the invisible forces powering modern society.
And, the macroscopic results are so reliable that they kind of mask the sheer chaos happening underneath.
Oh, for sure.
We see the heat, the light, the spinning motors, and we basically treat it as magic. But to truly understand the scale of the infrastructure that built the modern world, you have to zoom all the way down to the quantum mechanics of a single microscopic wire.
Right.
Everything we do, literally everything, scales up from that foundational atomic level.
Okay, let's unpack this. Because before we look at powering a city or even just like a single room, we need to establish the sheer staggering volume of what is actually flowing through your walls.
Yeah, the numbers are wild.
They really are. We often hear the term electric current, and casually we might picture this gentle stream of particles, but the actual mathematics of a single ampere of current are just mind-bending.
Absolutely.
The standard unit of charge is the coulomb, and a coulomb is not just a little cluster of electrons.
No, it is an almost incomprehensible number of charge carriers. I mean, 1 coulomb represents the collective charge of roughly 6 times 10 to the 18th power electrons.
That's 6 quintillion.
Right.
6 billion billion individual electrons. So when you have a device drawing just 1 ampere of current, that means 6 quintillion electrons are surging past a single cross-section of that copper wire every single second.
Yeah, every second. And the historical irony of how we model this massive flow is, well, it's one of the great quirks of early physics.
Oh, the convention thing, right.
Exactly. Electricity was being harnessed, measured, and utilized long before J.J. Thomson actually discovered the electron in the late 19th century.
Wait, really? They were building circuits without knowing what an electron was?
Yeah. The early pioneers knew a transfer of energy was happening, obviously, but they completely lacked the atomic model to see the physical particle. So they established convention. They just assumed current was the flow of positive charges moving from the positive terminal of a battery to the negative terminal.
Which, as we know now, is physically backward in a metallic conductor.
Completely backward.
Because the protons are locked in the atomic lattice. It's the negatively charged electrons that are highly mobile, moving from the negative pole to the positive.
Right. But rather than tear up a century of established diagrams and mathematical models, the scientific community essentially shrugged and just kept the convention.
That's so funny to me.
Yeah, we still map conventional current as positive to negative, even though the physical reality is the exact opposite.
Because the math works out the same, right?
Exactly. The mathematical models work perfectly either way, which is why the convention survives. But the deeper physical question isn't which direction they move, but why 6 quintillion electrons are moving in unison at all.
Right, because normally they just sit there.
Well, electrons in a passive copper spool aren't marching. They are in a state of random thermal motion, just zipping around at high speeds but going nowhere in particular. To get a current, you have to organize that chaos.
Which brings us to the concept of voltage. Now, the classic analogy is always water pressure, like a raised tank pushing water down a pipe.
Sure. The water analogy.
Yeah, imagine water in a perfectly flat tube. It doesn't move. You need a water tank at a higher level to create pressure. But that analogy breaks down when you consider the atomic reality, doesn't it? Gravity isn't doing the work here. We are dealing with an electrochemical gradient.
What's fascinating here is the precise thermodynamic nature of that push. We call it potential difference.
Okay.
A battery is not a storage tank of electrons. It is a chemical engine. It uses an internal chemical reaction to strip electrons from one terminal and force them onto another, actively creating a high-energy state and a low-energy state.
So it's building pressure.
Yes, it is manufacturing an electric field. And when we talk about a volt, we are actually talking about work. 1 volt is defined as exactly 1 joule of work being done to move 1 coulomb of charge between 2 points.
So the voltage is the metric of energy transfer. The battery is constantly expending its stored chemical energy to maintain that electric field, actively doing the work to shove those billions of electrons through the atomic structure of the wire.
Right. It is a continuous conversion of chemical potential
Yeah.
into kinetic and electrical energy.
Yeah.
And the electric field itself propagates through the wire at nearly the speed of light.
Oh, wow.
That's why the light turns on the instant you flip the switch.
Mhm.
But the electrons themselves, they're actually moving agonizingly slowly.
The drift velocity. I love this concept. While the push is instantaneous, an individual electron might only move a few millimeters per second.
Yeah, exactly.
Just like a tube completely packed with marbles. You push one in at the start, and one immediately drops out at the end. The signal is fast, but the individual marble barely moved.
That is the perfect way to visualize it.
Mm.
And the reason their actual forward progress is so slow is because they aren't traveling through an empty vacuum. They are fighting their way through a dense, vibrating solid material.
Which naturally leads us to resistance. Mm-hmm.
We all know Georg Simon Ohm gave us Ohm's law in the 1820s, establishing the linear relationship between the voltage pushing the current and the resistance slowing it down. V equals IR.
Right, the foundational equation.
But let's get into the mechanics of that physical resistance. What is actually happening to an electron trying to navigate a copper wire?
It is navigating a violently vibrating atomic lattice.
Violently?
Yes, because the metal atoms in the wire are arranged in a crystalline structure. At room temperature, those atoms possess thermal energy, which means they are vibrating in place.
Okay, so they're not standing still.
Not at all. As the electric field tries to pull the free electrons forward, those electrons are constantly colliding with the vibrating metal ions. They scatter, they lose momentum, they get pulled forward again, and they collide again.
I see.
This continuous microscopic friction is electrical resistance.
So if I'm an electron, running through a wire is like running down a crowded hallway.
That's a great way to think about it. A longer hallway, representing length, means I'll bump into more people. A wider hallway, representing cross-section, means I have more room to run.
Precisely. Geometry dictates the capacity.
But wait, if metals are so great at this, why are some better than others? Like, what's the difference between copper and iron?
The third factor of resistance is arguably the most crucial for modern engineering. It's the intrinsic nature of the material itself, known as resistivity.
Right, because if I make two identical wires, one out of copper and one out of rubber, the geometric properties are the same, but the behavior is wildly different.
Totally different.
Copper is an excellent conductor, and rubber is an insulator. But it's not just a slight difference in efficiency, is it? The scale of the difference in resistivity is kind of difficult to wrap your head around.
It really is.
Mm.
The atomic structure dictates the resistivity. In good conductors like silver and copper, the outermost electrons of the atoms are very loosely bound. They form a sea of free electrons that easily detach and drift when an electric field is applied. Their resistivity is incredibly low, down at the 10 to the negative 8th power range.
Wow. But in an insulator like glass or hard rubber, those electrons are locked down tightly in covalent bonds. They completely refuse to move.
Exactly. And the resistivity jumps to the 10 to the 12th or even 10 to the 17th power range.
We are talking about a difference of 20 to 25 orders of magnitude.
Yeah, it is an almost absolute barrier.
Which is exactly why you can have a high voltage copper line wrapped in just a millimeter of rubber, and you can hold it in your hand perfectly safely.
Mm-hmm.
The copper provides the frictionless quantum highway, and the rubber provides an impenetrable atomic wall that keeps the electric field from rerouting through your body.
And mastering that strict containment is what allows us to move from isolated batteries to complex, multi-layered circuit design.
So let's talk about the routing problem. We have the push of the voltage, and we understand the atomic obstacle course of the resistance. Now, how do we distribute this power throughout an entire building without causing the system to collapse?
Right. This is where it gets practical.
We have to look at the topology of circuit series versus parallel.
Because the physical layout radically changes the behavior of the electricity. Let's look at series circuits first. This is when devices are wired consecutively end-to-end, forming a single continuous loop.
So there is exactly one physical path for the current to take,
Correct.
which means the rate of electron flow must be identical at every single point in that circuit. It cannot bottleneck in one place and speed up in another, right? It is a unified flow.
Yes. But while the current remains constant, the voltage, the total push from the source, has to be divided among all the components.
Okay, that makes sense.
Each resistor in the sequence consumes a portion of that potential difference. And the total resistance of the entire circuit is just the sum of every individual obstacle added together, R1 plus R2, and so on.
We all know the classic frustration of series wiring from cheap fairy lights.
Oh, yes. The worst.
One bulb burns out, the physical pathway is completely severed, and you spend hours trying to find the one dead bulb because the entire string goes dark.
Yeah, we've all been there.
But the shared current is the real deal breaker for home wiring, isn't it?
It absolutely is. If we connect this to the bigger picture, the shared current is exactly why a series grid is impossible for a house. Think about the appliances in your house right now.
Okay.
A modern refrigerator and a small LED desk lamp have drastically different operational requirements. The fridge needs a massive flow of current to kickstart its compressor, while the LED requires only a tiny trickle.
So if you wired them in series, they'd be forced into a compromise. They would have to share the exact same current flow.
Exactly.
The LED would likely just explode from the excess, or the fridge simply wouldn't have enough power to turn on.
Which is why the parallel circuit is the foundation of modern infrastructure. Instead of one continuous loop, a parallel circuit uses branched connections.
It's like a river splitting off into multiple distinct channels that all eventually rejoin.
And the physics of those branches solve the entire distribution problem. In a parallel circuit, every single branch is connected directly across the main supply lines. This means the voltage, the electric pressure, is identical across every device. Your fridge, your lamp, and your television all feel the exact same 120 or 240 volt push.
But the current splits. It dynamically divides itself based on the specific resistance of each branch.
Yes, exactly.
The heavy-duty compressor offers low resistance to pull a huge current down its specific path, while the high-resistance LED pulls just the tiny fraction it needs down its own path. They operate completely independently.
Furthermore, and this is key, adding more branches in parallel intrinsically decreases the overall resistance of the entire system.
See, this is one of those concepts that feels counterintuitive at first. You are adding more resistors to the circuit, plugging in more appliances, but the total resistance actually goes down.
Right, because you have to think of it through the lens of conductivity. Every time you add a new parallel branch, you are opening up a brand new physical pathway for the electrons to travel from the high-pressure side to the low-pressure side.
Oh, I get it.
Even if the new pathway has high resistance, it is still an additional avenue. The overall bottleneck of the system decreases, which means the total current drawn from the source increases to feed the new demand.
And if your toaster breaks and snaps its internal wire, it only severs that one specific branch. The rest of the house doesn't even notice.
Exactly. It's an elegant self-balancing system.
Now, so far, we've been framing resistance mostly as a hurdle. It's the friction we have to overcome with massive voltage or, bypass with clever parallel routing. But here's where it gets really interesting.
Okay.
Usually when my electronics get hot, like if my laptop is burning my legs, it's a bad thing. It's wasted energy. But you're telling me we deliberately weaponize this heat.
Oh, absolutely. You enter the realm of joule heating.
Right. For a huge category of our appliances, generating intense, localized heat is the entire objective.
And the mathematics behind this are beautifully precise. James Prescott Joule established the law of heating, which states that the thermal energy produced in a resistor is proportional to the resistance, the time the current flows, and crucially, the square of the current.
I squared RT.
Exactly. H equals I squared RT.
The square of the current is the vital detail. That exponential relationship means if you simply double the current flowing through a wire, you don't get twice the heat, you get 4 times the heat.
Yeah.
If you triple the current, you get 9 times the heat.
Because you aren't just increasing the sheer number of electrons colliding with the atomic lattice, you are also increasing the energy behind those collisions. The atomic vibrations become violently intense, and that kinetic energy radiates outward as thermal energy.
But you can't just pump massive current through any standard copper wire to make a heater. The metal would just melt or oxidize, right?
Right, the engineering requires specific materials. This is where metallurgy meets electrical engineering. For heating elements in space heaters, toasters, or industrial ovens, we use specialized alloys like nichrome, which is a blend of nickel, chromium, and often iron.
Why nichrome instead of pure metals? Like, why not just use copper?
Two main reasons. First, nichrome has a significantly higher inherent resistivity than pure copper or iron, which guarantees a massive generation of heat when current is applied.
Okay, it makes sense.
Second, and more importantly, it has an incredibly high resistance to oxidation. If you get pure copper red hot in the presence of oxygen, it degrades rapidly, basically burns up. But nichrome can sit at an orange-hot glow for years without burning up.
Which is brilliant. But even a glowing toaster coil completely pales in comparison to the extreme application of Joule heating, the traditional incandescent light bulb.
Oh, the incandescent bulb is wild.
We rely so heavily on LEDs now that it's easy to forget how utterly insane the incandescent bulb actually is. We intentionally force so much current through a microscopic wire that it gets white hot and literally radiates visible light.
It is operating on the very edge of physical destruction.
Yeah.
To achieve that level of luminescence, without melting, the filament is made of tungsten. Tungsten is a remarkable element. It has a melting point of 3,380 degrees Celsius.
That is staggering.
It can survive temperatures that would turn almost any other metal into a literal liquid puddle.
But there is a massive problem with 3,000-degree metal. At that temperature, oxidation is instantaneous. If regular oxygen touches that tungsten filament, it will literally burst into flames and vaporize in a fraction of a second.
Which is why the glass enclosure isn't just for decoration. It is a highly engineered environment.
Right.
Originally, they used a pure vacuum. But engineers realized that at over 3,000 degrees, the tungsten atoms were actually sublimating.
Wait, sublimating?
Yeah, evaporating straight from a solid into a gas, coating the inside of the glass and thinning the wire until it just snapped.
So they changed the atmosphere inside the bulb.
Exactly. They fill the glass envelope with chemically inactive gases, typically argon or a mix of argon and nitrogen. These gases provide physical pressure to suppress the evaporation of the tungsten atoms, but because they are chemically inert, they refuse to react with the white-hot metal.
It is basically a captive star. It's a localized, perpetual near-combustion event, suspended in a cocktail of inert gas, perfectly balanced to shed immense heat and light without destroying itself.
It's beautiful engineering.
It really is. And speaking of destroying itself, we have to look at the opposite end of the spectrum, the fuse. This is an application of Joule heating designed specifically for self-destruction.
The fuse is a brilliant piece of sacrificial engineering. It operates on the same I²R principle, but its entire purpose is protection. It is a precisely calibrated piece of wire, often made from an alloy of lead and tin, which has an artificially low melting point.
And you place it in series with your main power line.
Right, the ultimate bottleneck.
Exactly. Under normal conditions, it handles the standard current perfectly fine. But if there is a short circuit or a massive grid surge, the current spikes.
Yep.
And because heat scales with the square of the current, the temperature of that fuse wire skyrockets instantly. Before that lethal current can reach your expensive appliances or, overheat the wiring in your walls, the fuse reaches its melting point, it liquefies, physically snapping the circuit open and stopping the flow of electricity dead.
It basically throws itself on the grenade to save the house.
It's a perfectly analog safety mechanism, but maintaining all these processes, the continuous push against the atomic lattice, the generation of 3,000-degree heat, the powering of massive compressors, it requires a staggering input of energy from the power grid.
The scale is massive.
Which brings us to the final reality check, the economics of electricity. How do we quantify this massive invisible effort, and what exactly are we paying the utility company for at the end of the month?
Well, we measure this expenditure in terms of electric power, which is the rate at which electrical energy is consumed or dissipated. P equals V times I. The standard unit is the watt.
Okay.
1 watt equates to exactly 1 joule of energy being consumed every second.
But a watt is an incredibly small slice of energy. When you look at your utility bill, you aren't billed in watts. You are billed in a macro unit, the kilowatt hour.
Right. The kilowatt hour or kilowatt hour is a commercial unit of pure energy. It represents the total energy consumed if you ran a 1,000-watt device continuously for exactly 1 hour. To put that in perspective of raw physics, 1 kilowatt hour is equivalent to 3.6 million joules.
That is a staggering amount of work. For context, lifting a medium-sized apple about 1 meter into the air takes roughly 1 joule of work. A single kilowatt hour is the energy equivalent of lifting 3.6 million apples.
That's a great visual.
And a standard household uses hundreds of these units a month. Like, A 400-watt fridge running 8 hours a day for 30 days consumes 96 kilowatt hours all by itself.
Yeah, it adds up fast.
It does, but here's the most profound paradigm shift of this entire topic. The source material has a fantastic more to know note here. There is a deeply ingrained misconception about what those kilowatt hours actually represent. When you plug in your phone or turn on your oven, you are not actually consuming electrons.
No, not at all.
Yeah.
That is perhaps the most persistent myth in consumer electronics. The grid is not a pipeline delivering fuel that gets burned up and vanishes.
So what does this all mean for the listener when they pay their bill? If I'm not buying electrons from the power plant, what am I paying for?
You already possess all the electrons you will ever need.
I do.
Yes. They are permanently embedded in the copper wiring of your house, in the coils of your toaster, and in the silicon of your television. You own the matter. What the power company provides is the potential difference.
They provide the push.
Exactly. They are maintaining the massive electromagnetic gradient. You are paying the utility board strictly for the energy required to push your own electrons around your house. You are paying for the work done to force your electrons through the violent atomic lattice of your appliances. The electrons do the work, transfer their kinetic energy as heat or light, and then cycle right back to the grid at a lower energy state to be pushed again.
You are renting the force, not consuming the particles.
That's beautifully put, yes.
It is a massive, closed-loop thermodynamic cycle. That completely changes how I look at a power line.
It changes everything.
Okay, to wrap up this deep dive, let's step back and look at the system as a whole. We moved past the simple water analogies to see the true atomic reality. We visualized quintillions of charge carriers fighting their way through vibrating metal lattices.
Mm-hmm.
We saw how parallel routing mathematically forces the grid to adapt to our demands, and we looked at the sheer extreme engineering required to trap 3,000-degree tungsten in a bubble of inert gas.
And we recontextualized the grid itself, not as a supplier of particles, but as a massive engine of potential energy. But, and this raises an important question, there's a final nuance here.
Oh, what's the nuance?
It's something that emerges when you combine the physics of the atomic lattice with the reality of Joule heating. We noted earlier that resistance is caused by electrons colliding with vibrating atoms.
Right.
And we know that as temperature increases, those atoms vibrate much more violently. Therefore, for almost all conductive metals, as the temperature goes up, the electrical resistance also goes up.
Makes perfect sense. The atomic obstacle course becomes more chaotic.
Now, apply that to the incandescent light bulb. When the bulb is turned off, just sitting at room temperature, the tungsten filament is cold. Its electrical resistance is actually quite low.
Okay.
This means the exact microsecond you flip the switch, there's very little resistance. A massive disproportionate surge of current, called the inrush current, slams into the filament.
Oh, I see where this is going.
But within milliseconds, that massive current violently heats the tungsten to over 3,000 degrees Celsius. As the temperature skyrockets, the atomic vibration goes off the charts, and the physical resistance of the filament surges exponentially.
Wow, wait, so the heat actively chokes off the current that created it.
Exactly. The skyrocketing resistance acts as a localized brake, instantly pulling that massive inrush current down to a steady, manageable operational level.
So the resistance of the bulb isn't just a static number printed on a box.
Not at all.
It is an actively shifting, self-regulating mechanism. The moment you introduce power, the environment changes, which changes the resistance, which alters the power. It is a continuous dynamic feedback loop happening in fractions of a second.
It is an ecosystem balancing itself in real time every time you flip a switch.
That is just incredible. So the next time you wake up and you push that plastic button on the toaster or you glance at the blank walls of your living room, remember the sheer scale of the quantum chaos happening just inches away?
It's always there.
Remember the billions of electrons, the vibrating atomic lattices, and the extreme thermal engineering that makes it all possible. You aren't just turning on a light, you are commanding a highly orchestrated, invisible force. Thank you for taking this deep dive with us. Keep questioning the invisible world around you.